Strange message. Okay. There's a strange window showing up in the middle of my screen, but I don't know if you see it or not.
Yeah, I do see that.
But I don't see anyone on my screen. Can you hear me?
We're here and we can see you.
But I can't see anybody.
Now, can you see everyone?
Yes. Okay, I think that's it now. I can see everyone and I have the slide. So
We can't see your slide, Joseph. We can just see your we can see your folder with the lecture slides, but we don't actually see your PowerPoint slide.
it says my screen sharing is paused. Did that help?
No. There, then, yeah, there we go.
Is that better?
That's better.
Okay, so refractories, and there's three properties that we'll consider: elasticity, brittle fracture, and creep deformation. So for elasticity, we'll start with some simple definitions of stress and strain and elastic constants. We'll define stored elastic strain energy, which is the driving force for brittle fracture. And we'll look at the effects of structure and temperature on mechanical properties of refractories. So for the definitions, a normal stress, sigma is the normal stress. It's just the force, F, the applied force, divided by the area perpendicular to the applied force. And the units for stress are PSI or pascals. And I put the conversion factors at the bottom of the slide. So 1 PSI, for example, equals 6.89 times 10 to the 3 pascals. And a pascal is a Newton per meter squared. So you'll see refractories, strength of refractories in PSI or pascals. So a simple diagram that shows the stress state, you have a cylinder, it has a cross-sectional area A, and you apply a force F. So if you elongate the cylinder and you put it in tension, it's a positive stress. If you compress the cylinder and put it in compression, it's a negative stress. So again, elongating the cylinder in tension is positive, and what you're doing is you're pulling the refractory apart by extending the bonds between the atoms. If you compress the cylinder, a negative compression, you're closing cracks in the refractory and you're pushing atoms closer together. So when you fracture a brittle material, brittle ceramic like a refractory, it occurs in the orientation such that the fracture plane is normal to the direction of the applied tensile stress. So brittle materials feel in tension because they're much weaker in tension than in compression. Associated with a normal stress is a normal strain. The normal strain is epsilon. That equals delta L over L0. So it's the change in length over the initial length. So LF is the final length minus L0, the initial length, divided by L0. It's a dimension over dimension, so it has no units. And the strains in brittle materials, like refractories, are quite small. So here's a diagram that shows the strain. L0 is the length of the cylinder on the left. LF is the length of the cylinder on the right, the final length after applying a force F, and then delta L is the change in length. The stress and strain are related, so you have a normal stress and a normal strain, and they're related through an elastic modulus constant, E, that's Young's elastic modulus. So the normal stress equals Young's elastic modulus times the normal strain. And since strain is dimensionless, the elastic modulus has the same units as the stress. So the units of elastic modulus are again PSI or pascals. So if you take that cylinder and put it in a mechanical test machine and apply a load, you get a stress strain curve that looks something like this. So we're plotting the stress versus the resultant strain. And if it's a linear elastic material, it obeys what we call Hooke's law, where the stress is proportional to the strain. So you have linear behavior. Most brittle materials fracture in this manner. So the slope of the stress strain curve is just the elastic modulus E. Sigma F is the fracture stress, and epsilon F is the fracture strain. So you have a linear curve until you have a brittle failure, and you have a fracture stress and a fracture strain. So those are normal stresses and strains. You can also have shear stresses and strains. The shear stress tau equals the force over the area. So tau is the shear stress, F is the applied force. And now this area A is parallel to the applied force. It's no longer perpendicular. Same units, PSI or pascals. So here's a cube that's loaded to produce a shear stress. So you have the opposite faces, you apply a force, and you know the area of the face. So you're applying a shear stress in this orientation. If you have a resulting shear strain gamma, that equals the tangent of theta. So we're looking at the side of the cube, and it's being distorted in this manner, or if you look at the dotted lines, and this angle is theta. So gamma equals the tangent of theta, which is theta is A over H. And the values of theta for brittle materials, the strains are really small. So you can approximate the tangent of A over H as just A over H. So gamma is the shear strain. A and H are these geometry dimensions. Theta is the angular change. And again, it's a strain, so it has no dimensions. So this value of theta on this diagram is a small number, just as it is for a normal strain. There's very little deformation in a brittle material prior to fracture. Just as we had an elastic modulus, we have a shear elastic modulus, and that's G. So tau equals G times gamma. Tau is the shear stress, G is the shear elastic modulus, and gamma is the shear strain. G, the shear elastic modulus, has the same units as E, PSI, or pascals. And if you load that cube and you measure the stress, the shear stress, and the shear strain, you'll get another linear behavior. And that's Hooke's law again for linear elastic materials. And now tau equals G times gamma. The slope of the curve is now G, the shear elastic modulus. And tau F is the fracture stress, and gamma F is the fracture strain. So we have normal stresses and strains, shear stresses and strains. And there's one more elastic modulus value that we need to consider, and that's Poisson's ratio. So nu is Poisson's ratio. It's the ratio of the transverse strain to the longitudinal strain. So if we have a cylinder that has an initial radius R0 and an initial length L0, the axial direction will be X and the radial directions will be Y and Z. And we apply a force, apply a load to this material, the cylinder, it becomes elongated. So we have a final length LF and an increase in length delta L. But the volume of the material remains constant. So it shrinks in the radial direction by an amount delta R. So we have an initial radius R0, a final radius RF, which is smaller than R0, and a decrease in the radius delta R. So Poisson's ratio is the ratio of the transverse to the longitudinal strain, or the strain in the Y direction divided by the X direction, or the strain in the Z direction divided by the X direction. Nu is Poisson's ratio. Epsilon transverse is the transverse strain. Epsilon longitudinal is the longitudinal strain. Poisson's ratio is dimensionless. It's the ratio of two dimensionless quantities. And the Poisson effect, basically, when you load the sample, the volume remains almost constant during an elastic deformation. So if it elongates in this direction, it has to shrink in this direction. So again, Poisson's ratio is minus the strain in the Y or Z directions divided by the strain in the axial or X direction, or in this case on this diagram, minus delta R over R0 divided by delta L over L0. There's always a negative here because there's a shrinkage in one dimension here. Poisson's ratio turns out to be a positive number, and it's always between 0 and 0.5. So those are the three elastic constants that we use for defining refractories. They're bulk elastic constants. And there's a relationship between the Young's modulus, the shear modulus, and Poisson's ratio. So nu equals E divided by 2G minus 1. So if you know any two bulk elastic properties, you can always calculate the third one. So when you load a brittle material, you will have an elastic strain energy. So you have a strain energy that's stored in the sample. So elastic strain energy is the elastic region where you apply a stress that results in a work being performed on the material. The elastic strain energy is essentially stored in interatomic bonds. So you have a cylinder of length L0, you apply a force to it, it elongates to LF, you have a certain delta L. So you perform work on that material, and the work equals the integral from 0 to L, force times dL. And if you solve that, work simply equals 1/2 times the volume of the cylinder times the applied stress and the resulting strain. So the elastic strain energy, you usually take the work divided by the volume, so you have this quantity U. U is the stored elastic strain energy per unit volume. It simply equals 1/2 times the stress times the strain. And in this case, we have normal stresses and normal strains. The units for the stored elastic strain energy are calories per cubic centimeter or joules per cubic meter. And why is this value of U important? Because that's the driving force for brittle fracture. So U is important because it's the driving force that is runs the fracture for brittle materials. And a simple way of looking at the stored elastic strain energy is just the area under the stress strain curve. So here's your stress versus strain curve. Here's your linear elastic behavior. The slope is Young's modulus. And the area under this curve at any particular strain or stress, 1/2 sigma epsilon. So that triangle that's in gray represents the stored elastic strain energy. So the higher the load or the higher the strain, the more stored elastic strain energy you have in the sample. So what factors determine the magnitude of the elastic modulus? The size of the cations and anions, and their valence. What's the charge on these cations or anions? So materials that have high elastic moduli, they have high bond strength and high bond density. So how you get high bond strength and high bond density, you have small ions, high charge, high valence, and they're in a crystal structure of dense packing. So we'll look at some examples of how the size and charge of the different ions in ceramic or refractory material affect the elastic modulus. I've listed here various materials, and going from bottom to top, we're going in the direction of increasing elastic moduli. So at the bottom are sulfides, fluorides, chlorides, and bromides. They have low elastic moduli. Oxides, and we mentioned these 6 oxides at the beginning of the introduction yesterday: SiO2, silica, Al2O3 alumina, MgO magnesia, CaO calcia, Cr2O3 chromia, and ZrO2 zirconia. That's where they fall on this scale. We mentioned nitrides, Si3N4 silicon nitride. They're a little higher. And then there's aluminides, brylides, borides, and at the top are carbides like silicon carbide. So carbides, nitrides, and oxides are your typical refractory materials, and that's where they fall relative to other materials. Grain size effects, well, there's no grain size effect for elastic modulus. Porosity has a big effect. The elastic moduli decrease with increasing porosity. And for a lot of these properties, people have developed empirical equations to describe how a property changes with porosity, maybe with grain size, and so on. So this one is Young's modulus as a function of porosity. So E0 is the Young's elastic modulus for a sample that has no porosity. Then it's e to the minus b times p. B is a constant, p is the volume fraction of porosity. So E equals E0 divided by e to the bp. And if you increase the porosity p, this denominator gets larger and larger as you increase p. It makes E smaller and smaller. So this is an exponential function, so the modulus drops off relatively quickly as you increase the porosity. The elastic moduli decrease with the increasing temperature. So here's an equation, another empirical equation that describes the decrease in elastic modulus with temperature. So T is the temperature, and this empirical equation takes E0 as Young's elastic modulus at absolute 0. And then as you increase the temperature, the elastic properties, elastic moduli decrease. In this equation, B is a constant, T0 is a constant. So E equals E0, your baseline elastic value, minus the constant times the temperature, and this is divided by e to the minus T0, a constant, and temperature. So if we rewrite it like this, E0 minus B times the temperature divided by E, T0, and the actual temperature. So you can see that T in this location or in this location, as you increase the temperature, they both have the effect on decreasing the elastic modulus. So some typical values at room temperature for a dense polycrystalline ceramic. A dense polycrystalline ceramic is going to exhibit brittle behavior, and so you're going to have a stress versus strain curve that is linear. Typical values for the fracture strength, sigma F, are about 50,000 psi. The strain to failure, epsilon F, is 0.001 or 0.1%. So the relatively small strain before failure takes place, it's a brittle material. The modulus on a lot of polycrystalline ceramics is about 50 million psi. So the ratio of E divided by G, the Young's elastic modulus divided by the shear elastic modulus, is about 2.5 to 1. Nu is Poisson's ratio. I mentioned that theoretically it goes from 0 to 0.5, but for most brittle materials, 0.2 to about 0.3 is a usual range. It may be a little lower than 0.2 sometimes, maybe 0.1. So this would be a higher performance polycrystalline ceramic. And if you look at a refractory with its heterogeneous microstructure and microcracks that are present, the strength and the elastic moduli are lower than these values. If you increase the temperature to intermediate or moderate temperatures, maybe up to 1,000 or 1,200 degrees C for a dense polycrystalline ceramic, your stress strain curve is most likely still going to be linear. It's still a brittle material, but the strength is going to start to decrease maybe 10 to 20%. The modulus is starting to decrease maybe 10 to 20%, and Poisson's ratio still remains the same, maybe 0.2 to 0.3. And when we compare a refractory to a higher performance polycrystalline ceramic, the strength and elastic modulus are going to be lower than for this dense material. So if we increase the temperature to temperatures greater than 1,000 or 1,200 degrees C, if we're looking at, again, a dense polycrystalline ceramic, the stress versus strain curve are going to start becoming nonlinear. So stress versus strain is now starting to become nonlinear, and the strength starts to fall off more rapidly. The Young's elastic modulus starts to fall off more rapidly, and that's because we're starting to have some plastic deformation or creep in either case here. So it's no longer linear elastic, and we're starting to have plastic deformation, and these properties start to fall off rather quickly. And for a refractory material, the drop in strength or elastic modulus is going to be much more rapid than for a higher performance polycrystalline ceramic. So here's a table that shows some typical values at room temperature. This is an insulating castable, a fire clay brick, a high alumina castable, 60% alumina, a magnesia carbon brick, which is the composite material, silicon carbide, silicon nitride. And I put a Portland cement concrete here as a reference. This is concrete, that's what your driveway or sidewalk was probably made out of. So here's E, G, and Poisson's ratio. So an insulating castable has a tremendous amount of porosity. So the Young's elastic modulus has about 800,000 psi. The shear modulus is about 400,000 psi. And Poisson's ratio is pretty low, 0.08. The fire clay refractories are generally around 2 to 3 million PSI for E, so this one's 2.4, and for G it's about 1, and Poisson's ratio is about 0.15. You get up to a higher strength material, a higher alumina content material, the elastic modulus and the shear modulus go up, 5.8 for E and 2.7 for G, and the Poisson ratio stays in the same range, about 0.12. The magnesium carbon brick is a resin bonded material with usually graphite and MgO, about 30%, usually carbon or graphite and the resin. It's cured at room temperature, so it's not a fired brick at this point. It has a Young's modulus of about 3.6 million, a shear modulus of about 1.6 million, and a Poisson ratio of about 0.15. Silicon carbide, this would be a fired ceramic, has a very high elastic modulus, 58 million, shear modulus of 26 million, and a Poisson's ratio of about 0.19. Silicon nitride is also very high in the elastic properties, about 60 million for E, 27 million for G, and Poisson's ratio about 2.21. And as a reference material, concrete is about 4 million for E, 1.8 million for G, and a Poisson's ratio of about 0.1. So that table shows some typical refractory materials. This is a plot of bending stress, would be probably a 3-point bending test versus the strain. So it's a stress strain curve, and it shows you what happens as you increase the temperature. And this would be for a dense polycrystalline ceramic material. So the uppermost curve here is at 20 degrees C. You can see it's linear. 400 and 800 degrees C at those temperatures is still linear. At 1200, it starts to become a little bit nonlinear. And the solid dots are where fracture takes place. So two things are happening here. As you increase the temperature, it becomes more nonlinear and the strength goes down. So by the time you get up to 1250, 1300, 1325, you can see these curves are bending over. Their materials exhibiting some type of plastic deformation. 1350, it's bent over even more, and in 1375, it's pretty much horizontal. It's just deforming until it finally fractures. And so these delta L over L's, this is 0.002. So this is Young's modulus versus temperature for a polycrystalline ceramic. This side of the curve, the solid line, is the Young's modulus. This side of the curve is the strength, modulus of rupture, and 3-point bending. And this is temperature. So you get a decrease in elastic modulus, a gradual decrease with increasing temperature, and then at some point you have this Nina curve and you have a rapid drop as you have plastic deformation, a rapid drop in the elastic modulus. For the strength, which is this dashed line, the strength sometimes shows a little maximum in the curve here. So it may rise a little bit, or maybe it may have a substantial rise. Then it starts to decrease normally, and then it falls off rapidly when there's plastic deformation. So what is happening here is usually some type of stress relief, and this is common in a lot of refractory materials. When you heat it up, stresses are relieved, strength goes up slightly. You may also be blunting crack tips and increasing the strength. Maybe there's some viscous flow and crack tip blunting and stress relief. So you'll commonly see a little bit of strength increase followed by the decrease, followed by a rapid decrease. And this is Young's elastic modulus for some different types of refractories. The one on the left is Young's modulus versus temperature. And on this plot, the open circle is a 60% MgO material that's direct bonded. So the MgO crystals are in contact with each other. It's probably, the balance is probably Cr2O3. There's a 60% MgO, again, that's direct bonded. So this one and this one. The square is a 90% alumina, and the triangle is a 70% alumina, fired refractory material. So the 70% alumina just has a gradual decrease in elastic properties with temperature followed by the rapid decrease. They all have a rapid decrease at some point when they reach a certain temperature. The other three, the 2 MgOs and the 90% alumina, have some stress relief that's taking place. So there's an increase in the elastic properties on those three, followed by the rapid decrease. The curve on the right is Young's modulus versus temperature for different kinds of monolithic materials. The open circle is a vibration cast material. The solid circle is a gun material. The open square is a low cement castable at 45% alumina. The solid square is a 45% alumina castable. Probably a conventional castable with a high cement content. And the triangle is a 70% alumina castable with a high cement content, probably. All of these are decreasing as you increase the temperature. So what's happening here is different than what's happening here, is that as you increase the temperature in these monolithic materials that have a cement binding phase, the cement dehydrates and you lose the cement bond, you destroy the cement bond, so it weakens, the modulus goes down, you create porosity. So those are contributing factors that show this decrease in elastic modulus. And if you continue to higher temperatures for these materials, this would turn around and the strength and the modulus would start to increase. And that's because you're starting to form a ceramic bond. So these materials were measured probably just below the temperature where they're forming the ceramic bond by sintering. So if this was continued to higher temperatures, you'd see a rise again in the elastic properties. So that's a typical fired refractory and a typical monolithic unfired refractory as a function of temperature. So there's several ways that we can measure the elastic properties. This first one is ASTM C1419. It's a sonic velocity method, and it gives you an approximate Young's modulus. It's not an exact value because you're estimating a Poisson's ratio in this test. So it measures sonic velocity in refractory materials and calculates an approximate value for Young's modulus. So the sonic velocity is measured through the length, thickness, and width of the sample. You don't have to do all those dimensions, but you can. Usually you just use the length, but you can measure it in any direction on a refractory shape. For the summary of this test, you have a velocity of sound waves passing through the sample. You know the length of the sample. So the sonic velocity is determined by measuring the distance through the sample, dividing by the time lapse between when the pulse enters the sample and leaves the sample. So you have the pulse time between the transmitted and the received pulse. So the longitudinal sonic pulse is a sonic pulse in which the displacements are in a direction perpendicular to the direction of the pulse. And the pulse travel time is the time required for the sonic pulse to transmit through the sample. This measurement is useful for research and development, engineering application and design. It's also a quality control method. It picks up porosity, it picks up defects, picks up cracks. So if there's a decrease in it's a simple test, and if you put a sonic pulse through the material and there's a decrease in the velocity, you know there's a manufacturing issue. And it can be used for purchasing specifications and data sheets. It's a non-destructive test, so samples can be tested and then used for other tests. The sample is a prism. Whatever length of the prism you have. And then what's important is the sides have to be parallel and smooth. So the ends of the sample have to be parallel and smooth. Well, I guess I just said it. Opposite surfaces across, whether you're doing a length, width, or thickness measurement, has to be parallel. And the sample size is important. The smallest dimension of the sample should be about 5 times bigger than the diameter of the largest aggregate in a refractory. Most refractories probably have aggregates, the larger aggregates about 1/4 inch. So a sample at least 1 inch or 2 in cross section and length will be adequate for this test. This is a calibration standard. This standard is 6 inches long. It's a piece of brass with an aluminum coating. And this is a transducer. Here's a second transducer. One is the pulsar, one is the receiver. And you simply put the transducer on each end of this standard, and you can go through a calibration using a known standard with a known travel time. And for the measurement, you just replace this standard with your actual refractory sample. For the equipment, you need a pulse generator in this frequency range, 0.5 to 2.5 megahertz. You need the transducers, which I just showed. One's an input, and one's a receiver, an output. And there's an oscilloscope. It may be built into the test machine that you purchase for this measurement. And a rough schematic of what this looks like. You have your sample, and on each side of the sample, you have your transducers. So you have a pulse generator that generates the pulse, and they both go to a dual trace oscilloscope, and you pick up the pulse location on the oscilloscope. It looks something like this. So the velocity of sound waves through the test sample is determined by measuring the distance of transmission, which is the sample length, and you divide that by the time lapse between the transmitted and received pulse. So that's the length divided by the time of transmission. So on an oscilloscope, you'll see this time displacement. This is where the pulse enters the sample, and this is where it leaves the sample. So you have this time, and that's your time of transmission. So very simply, you know the length of the sample, you know the time it took for the pulse to travel through the sample. So you can calculate your velocity V. So V is the velocity, and if we measure the sample length in feet, it's feet per second, and the traverse time is in seconds. So to calculate Young's modulus from the velocity measurement, the Young's modulus equals the density of the sample times the velocity squared. And this is where the approximation comes in on all these other terms. You have 1 plus Poisson's ratio times 1 minus 2 times Poisson's ratio, and then everything here in the numerator is divided by 1 minus nu. So nu mostly is between around 0.2, maybe between 0.2 and 0.3. So you pick a value of nu and you can calculate E based on the velocity squared. So it's an approximation, but since nu doesn't vary very much, it's not a bad approximation. So this is what a typical report might look like. You have the sample dimensions, length, breadth, and depth, the sample weight. You can calculate the density. Length, V meter, is the time, the transmission time in microseconds. And a V meter is a device made by this company, James Electronics. And that's a meter that you can purchase to measure sonic velocity. And then you calculate the velocity in feet per seconds. And then from the equation I just showed, you get an elastic modulus. And these are all around an average about 5.5 million PSI. The sonic velocity was about 12,000 feet per second. So that's a method used to approximate the elastic modulus. There's another method, ASTMC 1548, which gives you the exact values. You can get a Young's modulus, shear modulus, and a Poisson's ratio. And it's an impulse excitation method where you impact the sample, you create a vibration, you measure the frequency of that vibration, and you can calculate the elastic properties. So you measure a fundamental resonant frequency to calculate Young's modulus, shear modulus, Poisson's ratio, and it's called a dynamic because you're resonating the sample. There's another way of measuring an elastic property, and if you remember, we had a stress strain curve. The slope was the elastic modulus. You can actually, in the lab, test the material, get the stress strain curve, take the slope as your elastic modulus. It's a straightforward method. You have to be careful on how you measure the strains because they're very small numbers, so you have to use some type of strain gauge. And if you do a measurement like that, it's called a static measurement because you're measuring it under a load. This is a dynamic measurement. There's actually no load on the sample, you're just vibrating it. Turns out when you load a sample, the static measurements are a little bit lower than the dynamic measurements. So the dynamic elastic properties can be computed from the sample geometry, the mass of the sample, and the frequencies of vibration. So for this test, the fundamental resonant frequencies are determined by measuring the resonant frequency of the sample after you impact it with some type of impacting tool. The frequencies are measured with a transducer that's attached to the sample. And there's equipment that you can buy that are signal analyzers that will give you the frequencies. So you have an impulse and a transducer location, and you have different locations that give rise to different modes of vibration. And there's two modes that you need. You need a flexural mode and a torsional mode. The flexural mode gives you Young's elastic modulus. The torsional mode gives you the shear modulus, G. And once you have those two, you can calculate the Poisson's ratio. So the resonant frequencies, dimensions, and masses are used to calculate all three of these values, Young's modulus, shear modulus, and Poisson's ratio. This measurement is useful for research and development, engineering, application, and design. People that are doing stress analysis in refractory vessels by finite element analysis need the elastic properties. It's a quality control or process control test, and it's used in data sheets for product specifications. And again, it's a non-destructive test, just like the previous one. So you can use the sample for other types of tests. The sample is a rectangular prism. The length to the width has to be about 3 to 5, and the ratio of the width to the thickness has to be about between 2 to 5. So these ratios are set up by the derivations of the equations used to calculate the elastic properties, and their equations are valid over samples of these dimensions. We're assuming we have an isotropic, homogeneous, and linear elastic material when we make these measurements. This is a calibration standard. It's a piece of aluminum. It's the same size as a 9-inch straight, so it's 9 inches long, 4.5 inches wide, and about 2.5 inches thick. You can see it's sitting on a piece of foam, and that isolates the sample so that the vibrations, when you induce a vibration, it's not being damped out. So it isolates the sample. So this is a calibration standard, and you can also put a refractory brick of this shape and do the same measurement. So for equipment, you need some type of hammer or impulsor to strike the sample that induces the vibration. You need a transducer to pick up the vibration. It just transforms the vibration into electrical signal, some type of piezoelectric material. An electronic system, and that contains a signal conditioner, amplifier, signal analyzer, and the output is the frequency of vibration, and the support system, which isolates the sample, and so the vibrations are not damped, and that was that piece of foam under the sample I just showed. So this is what it looks like. You have a test specimen on a support system. This may be an impulsor, just a polymer rod with a steel ball bearing on the end, and you strike the sample with the impulsor, produces a vibration. The transducer picks it up, and the equipment, we use something called a grindosonic, which is a piece of equipment you can purchase. The output is the frequency of vibration. So if you want to generate a flexural resonant frequency, that's where the vibrations, displacements of the vibrations are in a plane perpendicular to the length of the sample. In that mode, you have nodal points that are 0.224 times the length from each end of the sample, where the vibration has zero displacement. So at the nodal points, you have zero displacement. The antinodal points between those nodal points, you have the maximum displacements. So you set up your sample with this type of support system, you strike the sample, and you record the resonant frequency. In the torsional mode, vibrations, the displacements are now in a cross section where they twist around the length of the sample. So it's a torsional vibration. And you place the sample on a support at its nodal points. And the nodal points are lines across the sample from the midpoint of the length and the width. And I'll show you that in the next few slides. Again, the nodal points have zero displacement. The antinodal points have maximum displacements. And same as for the flexural frequencies, you just strike the sample and record the frequency. So this should make it a little more clear. This is a flexural setup, and this is a torsional setup. Here are your nodal points on this sample. Here's an impact point. If you strike the sample right here in the center on the top, and you put your transducer on the side, you'll pick up the frequency in a flexural mode. So this is the same sample right here. Here's your strike point. Here's your, we use this point for the pickup. I guess you can use points here and here. But this is what the vibration looks like. You can see the nodal points and the maximum on the ends and in the middle. So this is vibrating perpendicular to the length of the sample. You can strike the sample on the side and the vibrations will be just in another direction perpendicular to this one. So this is again a flexural vibration. The nodal points for the torsional mode are these dotted lines. So your supports basically form an X, midway across the length of the sample and midway across the length. So the nodal points are on these dotted lines. And now you would strike the sample on the edge, either here or here, and pick up the torsional vibration over here. So this is an example of the torsional vibration that's twisting around the length of the sample. So that's how you get your two frequencies of vibration. And then there's some equations that are in the standard that you can calculate the elastic properties. So in this case, E is Young's elastic modulus. And if you use these units, metric units, your elastic modulus is going to be in pascals. And in this case, 1 Pascal equals 1.45 times 10 to the minus 4 psi. So E equals this constant, 0.9465 times m, which is the mass of the sample, f sub f squared. F sub f is the fundamental frequency in flexure, and that's divided by b, which is the width of the sample, and that's times L cubed, the length of the sample, divided by T cubed, the thickness of the sample, and T1 is a correction factor. So you know the sample's dimensions and mass, the frequency of vibration, you can calculate E. G follows the same type of format. The shear modulus equals 4 times L, which is the length of the sample. M is the mass of the sample. F sub T is a resonant frequency in torsion, divided by B, the width of the sample. T is the thickness. Now you have two constants here, B and A. So if you calculate E, calculate G, we have this relationship. We know two bulk elastic properties. We can calculate Poisson's ratio. So we now have exact values for each one of these. And this is what a typical report would look like. You have your sample dimensions, length, breadth, and width. The weight. Grindo is the just short for grindosonic. And if you look at the footnotes, that's the flexural mode with the nodal points at 0.22 L. So those frequencies are 432, other frequencies in the 400 range. Your correction factor comes from the standard. Your other constant comes from the standard. And it's a function of the sample dimensions and size. You have a measured E, a corrected E. Then you have your grindosonic reading over here in torsion we're using a foam pad. And you get your frequency values. They're a little less than 400. You have a correction factor and you can calculate G. It's about 2.6, 2.7. And these are in PSI. And you calculate your Poisson's ratio and correct it. And that's about 0.2. And your density on this material was about 132. So you have a Young's modulus of about 6.7 million, a shear modulus of about 2.7 million in PSI, and a Poisson ratio of about 0.2. So those are two methods that are pretty easy to use to get the elastic properties. So we've gone over Young's modulus, shear modulus, Poisson's ratio, and typical methods of measuring them. The next section is on brittle fracture, and we'll talk about theoretical strength, the stress criterion versus the energy criterion for failure, and then how some structural aspects affect fracture. So there's an equation that describes the theoretical strength of brittle materials. So sigma C is the theoretical strength, E is the elastic modulus, gamma S is the fracture surface energy, and that's the energy of a fracture surface. When you create a fracture surface, you have excess energy relative to the bulk of the material. So that's the fracture surface energy. And A0 is the interatomic spacing. So the theoretical strength just equals the elastic modulus times the fracture surface energy divided by the interatomic spacing, and that's to the 1/2 power. So it's the square root of this term. So if you have a high strength material, again, just like for elastic modulus, you need high bond strength and high bond density. You need small ions, high charge, or high valence, and dense packing in a crystal structure. So when you have a high strength material, you're also going to have a material with a high elastic modulus. So if you look at theoretical strength of a brittle material like a refractory or an advanced ceramic, and you compare it to the actual strength you measure in an experiment, it's quite different. So Al2O3 alumina has a theoretical strength of about 5 million psi, but when you measure it, you might get 30,000 to 50,000 psi, quite a bit lower. Silicon carbide has a theoretical strength of 6.8 million psi, but a practical strength of maybe 25 to 100,000 psi. And then glass has a theoretical strength over 1 million psi, but when you measure it, you're lucky to get 15,000 psi. So why is there a big difference in these two? Well, all of these materials have flaws. The flaws are stress concentrators, and it causes a fracture at loads much below than the theoretical strength. Flaws are pores. I mentioned that most refractories have 10 to 20% porosity. I mentioned that they were microcracked. So pores and microcracks are flaws. You can damage the surface just by touching it or rubbing it with another refractory sample. And an example with glass, I used to make glass fibers in an environmental chamber and test the strength virtually without touching them. And the strengths are in this range. You can measure these strengths under pristine conditions, but as soon as you touch the fiber or even a piece of dust impacts it, you're back down to this strength. So the stress criterion simply says that you have stress concentrations at these flaw tips of the defects, and that reduces the theoretical strength. So we'll take up a plate and we'll put a flaw in it in the shape of an elliptical hole. So here's a ceramic material, a plate. We put this elliptical flaw in it. The minor axis is 2H. The major axis is 2C. There's a radius of curvature rho at the tip of this ellipse. And then we apply a load, sigma A, sigma applied to the sample, perpendicular to this flaw. And if you plot the stress as a function of distance from the tip of this ellipse, you'll have a maximum stress concentration right at the tip, and then it falls off as you approach the surface to sigma A, which was the applied stress. So you have a stress concentration at the tip of this ellipse. And there's an equation that describes that maximum concentration. Sigma max equals 1 plus 2 times C divided by H times the applied stress. 2C is the length of the ellipse, 2H is the height of the ellipse. They're the dimensions of the ellipse. A rho is the radius at the tip of the ellipse. It doesn't enter into this equation at this point. So sigma max is usually at least 3 times sigma applied for this ideal flaw in the material. But it turns out that we don't have elliptical shaped flaws in our refractive materials. We have atomically sharp cracks. So that increases the stress rise at the crack tip. So the equation that describes that type of crack with an atomically sharp crack, sigma max equals 2 times C divided by rho to the 1/2 power times the applied stress. 2C is the length of the crack. Now, rho is the radius of the crack tip. So it turns out this ratio of the length of the crack to the crack tip is very much greater than 1. It's a large number. So when you have a large ratio here, there's a very high stress concentration. So maybe 100 to 2,000 times. So the stress is concentrated 100 to 2,000 times at an atomically sharp crack. And we noticed from previous discussion, all the microcracks present in a refractory, that gives rise to a very low strength material. So in general, refractory materials are quite low in strength. So the stress criterion, which we just discussed, simply illustrates that a stress is increased around the flaw. So it tells you how much the stress is increased, but it doesn't tell you when that crack will grow and you have failure. So the other criterion is the energy criterion. That gives you information as to when the crack will grow. So a flaw will propagate when the decrease in the stored elastic strain energy associated with the crack extension exceeds the increase in surface energy associated with a new crack surface. So we talked about stored elastic strain energy. That's the driving force for brittle fracture. So the stored elastic strain energy is simply converted to fracture surface energy. So when the strain energy exceeds the fracture surface energy necessary for a crack to grow, you have failure. So this does show the necessary conditions for crack extension, and that's this well-known equation known as the Griffith equation. So the strength, sigma F, the stress level required to propagate a crack of a certain flaw size C star, so this is the failure stress, equals 2 times gamma S, which is the fracture surface energy. Elastic modulus is in this equation. E is Young's elastic modulus. That's divided by pi times the critical flaw size, and that's all to the square root of 2. So a simple plot that illustrates this, if you plotted energy versus crack size, this linear relationship shows a surface energy as a function of crack size. So that's your gamma S term. This curve shows the stored elastic strain energy. That's minus the applied stress squared divided by E. So as you increase the stress, you increase the stored elastic strain energy in that direction. If you sum these two, you get the total energy and you get a curve with the maximum that looks like this. The maximum corresponds to that critical flaw size. So as you apply more and more stress and you reach a stress in this location here, where this stored elastic strain energy is now bigger than the surface energy at this critical flaw, you have failure. So that's how the stored elastic strain energy relates to the surface energy and this Griffith equation. So for fracture to occur, you must reach a stress big enough to propagate a crack, the critical crack that's in the material C star. The energy of the system is lowered when the crack grows. The strain energy is then converted to fracture surface energy. So that's how refractories and brittle ceramics feel. The strength is much lower than the theoretical strength because flaws are present. So flaws can be pores. So the effective porosity, they decrease the cross-sectional area that's available to carry the load, plus they concentrate stress. So if you measure strength versus volume fraction of porosity, you see this rapid drop off in strength as porosity increases. It's an exponential decrease in strength with increasing porosity. So there's a lot of empirical equations that describe the effect of various values on elastic properties and strength. This is another empirical equation for the effect of porosity. The fracture strength equals a constant sigma 0 e to the minus b times the porosity p. Sigma 0 and b are constants. If you just rearrange the equation and put e to the bp in the denominator, it's just this constant divided by e to a constant times the porosity. So as you increase the porosity, this number increases exponentially, and therefore the strength decreases rapidly also. You can take a material and run an experiment where you vary the porosity and measure the strength. And if you do that, you can plot the log of the strength versus porosity. So you take your equation, which I just described, you take the natural log of each side of it. So you get the natural log of strength equals the natural log of this constant sigma 0 minus b times the porosity. So b is the slope, ln sigma 0 is the intercept. So you'll get a straight line. You'll have an intercept, so you can calculate sigma 0. You'll get a slope, so you can calculate b. And then you can put them back into this equation and calculate the effect of porosity on strength for a particular material. Grain size is important because it's related to flaw size. I mentioned that microcracks they develop around the different grain sizes that you have in the refractory. So if you have a large grain size, maybe a 1/4 inch, the expansion mismatches are going to give rise to probably a microcrack on the order of the grain size. So grain size is related to the flaw size because of the microcrack situation. So here's the Griffith equation. The strength equals 2 times the fracture surface energy times the elastic modulus divided by pi c, the crack length, to the 1/2 power. You can simply substitute the grain size, the grain diameter, for the flaw size. So now d is substituted for c, and the strength is a function of the grain size or diameter of the grains in a refractory material. So d is in the denominator. The bigger the grain size, the bigger the flaw size, the lower the strength. So strength is proportional to 1 over the grain size to the 1/2 power, or simply the strength equals a constant sigma 0 d to the minus 1/2. So bigger grain size gives you a lower strength. Strength is proportional 1 over d squared. I just gave this equation, sigma f equals sigma 0 d to the minus 1/2. If you take the log of each side of that, you have the log of the strength equals the log of sigma 0, which is a constant, minus 1/2 the log of the diameter. So the intercept, if you do a log sigma f versus log d plot, basically plotting strength versus diameter, you get a straight line. The intercept is log of sigma 0, so you can calculate sigma 0. The slope is minus 1/2. And that's a typical relationship you'll see in a ceramic material or a refractory ceramic material. You get a slope of minus 1/2. So the bigger the grain size, the lower the strength. So this is just a table of some typical properties for polycrystalline ceramics. Al2O3 is a refractory material. BeO we mentioned as a material, but it's beryllium oxide, which is a toxic material. MgO, Cr2O3, this is a spinel, MgAl2O4, this is mullite, Al6Si2O13, this is phosphorite, Mg2SiO4, and this is zircon, ZrSiO4, a boron carbide, a silicon nitride, aluminum nitride, and a boron nitride. So some typical ceramic and refractory materials. Just looking at a few of these, the MOR for alumina, and it's got a small grain size, so it's a high performance ceramic. It may be about 65,000 PSI, 400,000 PSI for the compressive strength. The elastic modulus is about 60 million PSI. The shear modulus is around 23 million PSI, and Poisson's ratio is around 0.27. Another one, silicon carbide, has a high MOR or strength, about 60,000 PSI, a high compressive strength, about 200,000 PSI, a high modulus, about 70 million PSI, 29 million for the shear modulus, and about 0.2 for Poisson's ratio. And a mullite material, maybe 25,000 PSI for the strength, 190,000 PSI for the compressive strength, and elastic modulus about 25 million PSI. So there's a table for some typical ceramic materials, and these are the properties we just talked about: strength, compressive strength, Young's modulus, shear modulus, and Poisson's ratio. So if you look at strength versus temperature for some refractory materials, the open circles are an alumina silica refractory, while the open and closed circles are alumina silica. The squares, whether open or closed, are basic refractories. The triangle with the point up is an alumina zirconia silica refractory known as AZS. The one with the point down is silicon carbide, and this one has to be a nitride, silicon nitride bonded silicon carbide. You can see there's the aluminum materials tend to be in the center, the basic refractories tend to be up here, and the silicon carbide is up here. But the alumina silica materials are all showing, not all of them, but some of them are showing this slight increase prior to a more rapid decrease where there's some type of stress relief. This is a 90% alumina, 9% chrome material, which just shows a constant decrease. Silicon carbide is still increasing with strength. We're not measuring at a high enough temperature where deformation would take place. And all these basic refractories, for the most part, are slowly decreasing with strength, except for this one here, which is showing some stress relief. So that's what you'll see for most refractories, maybe a slight rise in strength due to stress relief, followed by a rapid decrease in strength when you get close to their use temperature. Castables are a little bit different. So these are a series of castables, and the numbers represent the alumina contents. So you have strength versus temperature. And castables, I mentioned that as you heat them up, you degrade them because you destroy the calcium aluminate cement bond, you dehydrate the cement, you weaken the bond, you create porosity, so you decrease the strength. And then at some point, you start sintering the material and densifying it, creating a ceramic bond so the strength goes back up. And then again, you'll reach a point, depending on the chemistry of the material, where it starts to deform near its use temperature. There is a series of ASTM tests that you can use to measure compressive strength and bend strength or flexural strength. So ASTM C133 is a common test that's used all the time to measure room temperature compressive strength. And it's in the refractory industry, for some reason, they call it cold crushing strength. And flexural strength is the 3-point bend test, also known as the modulus of rupture. So why is the strength values important? Cold strength of refractory is an indication of its suitability for use in construction. You need a material that's strong enough to go through the construction phase. However, it's not a measure of performance at elevated temperatures. So you can have a very strong room temperature material and it can be very weak at elevated temperatures. So that cold strength does not reflect its high temperature behavior at all. Cold strength is useful in research and development, in engineering applications, in quality control. It's a good way to measure if your product was made correctly, if it meets the right strength, and it's used in data sheets for purchasing specifications. So we'll do cold crushing strength or compressive strength first. For refractory materials, it's divided into two groups. If the bulk density is greater than 100 pounds per cubic foot, you use a certain sample size and certain test conditions. And if the bulk density is less than 100 pounds per cubic foot, you have a different size sample. So denser materials, you use a smaller sample, a 2-inch cube, or a 2-inch diameter cylinder, 2 inches high. If it's a weaker material of lower density, you use a larger sample, usually a half of a 9-inch straight, which is about 4.5 by 4.5 in cross section and 2.5 or 3 inches in thickness. This is a typical cold crushing cube. It's 2 inches on a side. So that's what a typical sample would look like. For the equipment for this, you need a mechanical test machine. And there's two types of test machines. One is a hydraulic test machine, one is a screw-driven test machine. In the hydraulic system, you increase the stress, so you're measuring at a stressing rate. And the screw machine, you're applying it, the load in terms of a displacement. So that's a displacement rate test. You need a spherical loading block, which has to have an area greater than the cross section of the sample. So here's your loading blocks in your test machine. Here's your sample. And because the samples are generally just diamond cut, you're using a bedding material to provide a uniform load to the sample. And then you have a spherical loading block, which accounts for, makes it a more uniform load in case the surfaces aren't exactly parallel. It conforms to the sample dimensions. So if you have a denser material greater than 100 pounds per cubic foot, use a bedding material, and that's usually masonite. It's a soft particle board. If the bulk density is less than 100 pounds per cubic foot, you're going to apply the load directly to the face of the sample. And there are different loading rates for different size samples. And this is right out of the ASTM standard. So the top part of the table is for dense materials greater than 100 pounds per cubic foot. They're usually going to have less than 45% true density, true porosity. True porosity is a combination of open and closed pores. A typical sample is 2 by 2 by 2 or 2-inch diameter by 2 inches tall. This is the area that's actually loaded. This is the loaded cross section. So the cross section is 2 by 2 or 2-inch diameter. The loaded area is 4 square inches or 3.14 square inches. If you're doing a stressing rate, this test calls for 17,050 pounds per inch squared per minute, so PSI per minute, which gives a loading rate of about 7,000 pounds per minute or 5,500 pounds per minute. If you're doing a screw-driven machine where you're loading according to displacement, the strain rate is in this case would be inches per minute, 0.05 or 0.05. And for a less dense refractory, less than 100 pounds per cubic foot, which would have a true porosity usually greater than 45%. You're using the bigger sample, a 4.5 by 4.5 by 2.5 inch sample. You're loading it on the large face 4 by 5 by 4.5. The loaded area is about 20 square inches. You want a much bigger sample because it's a much weaker sample. You get a better measurement that way. You're loading at a lower stress rate now, 435 PSI per minute, which is about 8,800 pounds per minute. And if you're running a strain rate experiment, you're going to do it at about 0.05 inches per minute. So that is for compressive strength. So a sample is loaded to failure. And how you decide it failed, well, it fails to support the load. It completely disintegrates. Or in some cases, there's a reduction in sample height. It does not disintegrate. So when the sample height decreases by 10%, well, that's considered failure. You calculate the cold crushing strength S, and this is in pounds per inches squared. You just have the load W in pounds divided by the area of the sample, A. And you can average the top and bottom surfaces and get the area that way. So a very simple test. And here's a report for a zirconia sample. This is probably a higher strength zirconia sample that might have been maybe in a slide gate or some application like that. But it must have been a small sample size because the samples that were taken out of there are small cubes, about 0.6 by 0.6 inches. So they're much smaller than the required 2-inch size, but they were probably the largest size samples we could get out of the piece that was supplied. So the cross section, breadth and depth, the maximum load, in this case was about 15 to 19,000 pounds, and the calculated cold crushing strength, and averaged about 39,000 PSI. And the standard deviation is always high on these tests. This is about 5,000 PSI. Strength tests on refractory materials, whether it's compression or flexure, usually have a pretty high variation because they're heterogeneous materials. And then this one was just another material that was measured. So I think we'll stop there. We're about halfway through. We'll finish up with this other part of the test. We'll do high temperature strength and a tensile strength test, and then we'll finish up with the section on creep. So I think we'll just take a break now. Can you hear me?
Yeah, I can hear you.
I can
Okay.
hear you.
Yes.
All right, I just want to make sure. So we're in the middle of the normal an ASTM strength test, C133 for normal cold crushing and modulus of rupture or bend bar samples. And the second part of this test is MOR or modulus of rupture. It's just a 3-point bending test, which is one of the most common strength tests in the refractory industry. It's divided just like the compressive strength, bulk density greater than 100 pounds per cubic feet and bulk density less than 100 pounds per cubic foot. The MOR sample for the denser samples can be a full-size brick, which is a 9-inch straight, 9 by 4.5 by 2.5 or 3 inches thick, or a 9 by 2 by 2 inch bar, or a 1 by 1 inch by 6 inch bar. If it's a less dense material, it's a full-size 9-inch straight, again, 9 by 4.5 by 2.5 or 3 inches. This is what a broken bar looks like. This is a 1 by 1 by 6 inch bar. And these are diamond cut surfaces, and you can see that it's not a polished surface, it's just diamond cut, but you can see the different types of coarse aggregate in the ceramic matrix. So you need a mechanical test machine, and we talked about hydraulic test machines and screw-driven test machines. The hydraulic is a stress rate machine, and the screw is a displacement rate machine. You need a 3-point bend apparatus where the bearing surfaces are greater than the width of the sample and a means for alignment. So this piece that's crosshatched on the top and bottom are the loading plates of the test machine. Your sample here is in the middle, and there are 3 rods for 3-point bending. If you look at the side view, the bottom rods have a pivot so that they can align with the sample in case it's not perfectly flat. So the procedure is divided up into dense materials greater than 100 pounds per cubic foot and materials less dense than 100 pounds per cubic foot. And the loading rates for these different densities are as follows. For the denser materials, you have the full-size brick, the 9-inch straights, the 9x2x2, and the 6x1x1. The spans for the 9-inch long ones are 7 inches and 5 inches for the 6-inch long one. And the stressing rates are always 1,305. That's PSI per minute. And that gives a loading rate based on the sample size in pounds per minute, ranging from about 5,000 down to 174, depending on the sample size. And the strain rates are always 0.05 inches per minute. Same size samples for the less dense materials, the 9-inch straights and the 9x2x2, except there's no 6x1x1 bar. In this case, the spans are 7 inches. The loading rates are much lower, 435 PSI per minute. And these are the pounds per minute from about 1700 down to 331, and 0.05 inches for the strain rate for a screw type machine. The samples are loaded till failure. A crack will develop at mid-span and it won't hold the load anymore. The formula to calculate strength in 3-point bending is 3 times the load at failure times the span between the lower supports divided by 2 times B, the width of the sample, and then the thickness of the sample squared. You put everything in pounds and inches, you get MOR, or the 3-point bending stress in PSI. Output, a report would look like this. This sample had a 5-inch span tested on a displacement type machine at 0.05 inches per minute. The cross section was approximately 1 inch by 1 inch. These are the loads. The MOR average was 211 in this case for the samples at the top here. And the standard deviation is 71. So you can see how variable the answers are for a refractory material. The ASTM test calls for 5, an average of 5, whether it's compression or a 3-point bending. That's probably inadequate, but that's what the test calls for. So the 3-point bend strength test at room temperature, again, it tells you how strong it is at room temperature, but it doesn't give you an indication of how well it holds up at high temperatures. So there's another test, C583, which is the MOR, or modulus of rupture at an elevated temperature. So it's a 3-point bending test at temperature. You can do fired bricks or monolithics. You're generally running an oxidizing atmosphere, and you're doing this at a constant stress rate. The significance of this test, well, it's an accepted method to evaluate materials at service temperatures. It's one of the most common tests to see its performance at high temperatures. And it's in data sheets, and you write specifications based on this test. The test size is usually a 1 by 1 by 6-inch sample. Sometimes it's a little larger, a 2 by 2 by 9-inch sample. Again, on this test, the opposite faces should be parallel, adjacent surfaces should be perpendicular. So you're usually cutting this with a diamond saw out of a larger piece. Here's a smaller 1 by 1 by 6-inch sample, fractured at high temperature, and it's slightly off center on that fracture. Ideally, you want the fracture right in the center, but again, these are heterogeneous materials. They may not always behave normally. The mechanical test machine can be hydraulic. It can be a screw-driven machine for displacement testing. And it can be other. There's a lot of other versions of machines using lever arms and different ways of loading it. But the best ways are to use a mechanical test machine, whether it's hydraulic or screw-driven. The furnaces for these machines, sometimes they're usually electric, but sometimes they're gas. And the bearing surfaces that apply the load to the sample have to be another refractory material that's volume stable and doesn't react with the samples. So here's a schematic diagram of the test setup. Your sample is measured in 3-point bending. Here's your sample, the 2 bottom knife edges for the support and the top knife edge for applying the load. There's a furnace surrounding the sample, and this is sitting in some type of mechanical test machine where you can apply a load to the top ram. There's different rates for heating specified by this standard. You don't want to heat the sample too fast and thermally shock it. So they're specifying 600 F per hour to about 1800 F. And then if the test temperature is higher than that, not to exceed 200 degrees F per hour. If you're testing a refractory that's already been fired, it specifies a 3-hour minimum hold prior to testing. If it's unfired, it's specifying a 12-hour minimum hold. And that's where some of the sintering and densification will take place to stabilize that material if it's unfired. The samples are loaded to failure at midspan. There's only one loading rate, 175 pounds per minute, or the stressing rate is 1312 psi per minute. The formula for calculating the strength is the same as for the room temperature version. It's just 3 times the load times the span of the lower supports divided by 2 times the width of the sample times the thickness of the sample squared. Exact same formula, only difference is it was measured at a higher temperature. So here's what a report might look like. This one was actually tested on a 5-inch span in a screw-driven machine at 0.05 inches per minute. The test temperature was 2800 degrees F. There was a 5-hour hold. It was a 1-inch by 1-inch cross-section sample. And these are the final loads and the calculated MOR. In this case, it was 431 with the standard deviation of 51. Still quite a bit of variation. So we described a compressive test, which is in pure compression. We described a 3-point bending test, which is in a combination of tension and compression. The bottom surface is in tension, the top surface is in compression. So there's also another test, C496, which is approaching a pure tension type test. So it's the splitting tensile strength of a cylindrical sample. So if you want to get something close to a pure tension test, you would use this splitting tensile strength test. So a diametral compressive force is applied along the length of the cylinder until failure occurs. If you load it in a diametral way, it induces a tensile stress in the plane containing the applied load. It's a simple method. It can give you a relatively pure tensile test result. The geometry is just a cylinder. It's very simple. There's no special fixtures other than the loading plates of the test machine. It's almost in pure tension, but not quite. So it's going to be slightly larger than if you had a pure tensile strength test. But it's still going to be much lower than the MOR test because that's in a combination of testing and compression. The sample is cylindrical and the length to diameter ratio, L to D, is usually between 1 and 2. So here's a cylinder for a dimensional compression. It's been core drilled with a diamond core drill and the ends are cut with a diamond blade. It's 2 inches long and about 2 inches in diameter. Mechanical test machine, again, can either be hydraulic or screw driven. And you're going to have a spherical loading block same as you run the compression test. And that has to be a bearing block greater than the size of the sample. You apply a load at a constant rate. Is usually between 100 and 200 psi per minute until failure occurs. And you're going to have to use a bedding material. Masonite, I mentioned, a kind of a soft composite board or even a plywood will work. And this is what the setup looks like. You have your loading plates up on top and underneath. This one doesn't show a bedding material, but you can put a bedding material between the loading plate and the sample. This is your cylinder. The diameter is D, the thickness is T. And when you load a sample along a diameter like this, along this dotted line, you develop tensile stresses that pull the sample apart in the horizontal direction. So it breaks in tension along this dotted line. So the calculation for the tensile strength, S is the splitting tensile strength in PSI, 2 times P, which is the applied load at failure, divided by pi. L is the length of the cylinder, and D is the diameter of the cylinder. So it's a relatively simple test to run, no special fixtures to get a tensile test of a refractory. Here's an example of a report. The loading rate was 0.05 inches per minute. No loading pads were used. The sample was about 3/4 of an inch long and 1 inch in diameter. Again, it's not a 1-to-1 ratio. We were probably limited in the amount of material we had. Here's the maximum load, about 18, 19 pounds, and your tensile strengths, relatively low, about 16 or 17. The scatter is a little better on some of these tensile tests than on the bend bar type tests. So that's the finish of the strength or brittle fracture section. The last section is creep. So we'll discuss creep fundamentals, and then we'll look at how the structure affects the creep behavior. So to define creep, a creep is a time-dependent deformation at an elevated temperature. Usually takes place at temperatures greater than half the melting point. And that's where the stress strain curve is no longer linear, where you're having some type of plastic deformation. So it's time dependent at temperature and usually at relatively high temperatures where the behavior is nonlinear. And this is what a typical creep curve looks like. You have deformation or elongation versus time. There are 3 regions of the creep curve. There's actually a beginning region here that's an elastic extension that's not really part of creep, but when you load a sample and apply the load for the creep curve, you're going to have an elastic extension, and then you're going to start the 3 regions of creep. The primary creep region, where you have a decreasing creep rate, the secondary or steady state creep region, where it's linear, and then the tertiary or final stage of creep, where it accelerates and then it leads to failure. So if this is usually the long time region, the secondary region, and that's where you can do a lifetime prediction of how long a sample might last. So there are 3 stages of creep behavior. The primary creep region, the first region, the change in strain with respect to time, it's a decreasing rate, so the rate of creep is decreasing. In the secondary creep region, the change in strain with respect to time is constant. So that's that linear region where you have steady state creep. And the last stage of creep, the third region, the strain rate with respect to time, that's increasing or accelerating, which leads to failure. So if you increase the temperature or you increase the load, you have a greater strain to failure and a shorter time to failure. And that looks something like this. If you plot elongation versus time, if you go in this direction, following this arrow, you're increasing the load or you're increasing the temperature. So as you increase the load or temperature, you can see that these are the failure points. The time to failure is shorter and the amount of deformation is larger. So where most of the modeling takes place is in the secondary creep region. That's the region that's been studied extensively. That's the steady state region. And an equation has been developed to describe creep in that region. So the strain rate, the epsilon dt under steady state conditions, equals a constant A, 1 over grain size, GS is grain size, and A is the grain size exponent. So it's 1 over grain size to a power A times the applied stress to a stress exponent N. So N is the stress power law exponent times E to minus Q over RT. Q is your activation energy for creep, R is the gas constant, and T is temperature. So this equation takes into account grain size, the applied stress, and the temperature that you're running the test at. So you can isolate each one of those components. And if we look at the stress first, we'll look at the stress exponent. So this was the equation I just described. If you hold a grain size constant and you hold a temperature constant, you can run an experiment where you can measure the strain rate, the epsilon dt, as a function of applied stress. So holding grain size and temperature constant gives rise to this equation. The strain rate, the epsilon dt, just equals a constant, which now includes the grain size and temperature, times stress to some exponent n. If you take the log of each side of that, you get the log of the strain rate equals the log of a constant plus n, the strain rate exponent, times the log of the stress. So the log of the strain rate plotted against the log of the stress is this type of plot. The slope, this value n is the slope. So you can run this kind of experiment, measure creep at various stresses, and come up with the stress exponent n. So n is important because n tells you what the physical process is that's causing creep of that particular refractory material. So there's all type of models that you can derive that have the different n values. So if n is 1, it's going to be a diffusional or viscous flow creep process. If n is 2 to 3, it's going to be a grain boundary sliding process. If n is 3, it's going to be a dislocation process. So you can run this experiment, determine n, determine the type of creep you have in your material, and maybe from that you can maybe redesign your material to try to avoid that process. We can isolate the temperature or the activation energy. So if we hold the grain size constant, this is our regular or normal creep equation, holding the grain size constant, holding the stress constant, but varying the temperature, we end up with this equation where the constant has the grain size and the stress in it. So the strain rate equals a constant E to the minus Q over RT, taking the natural log of each side of that equation. The natural log of the strain rate equals the natural log of a constant minus Q over RT. Plotting this, the natural log of the strain rate versus 1 over T, 1 over the temperature, you get a straight line, and the slope is Q minus Q over R. R is the constant, the gas constant, so you can calculate the activation energy. So increasing temperature is from right to left on this, which gives increasing strain rate. So the slope is Q, and that's an activation energy that's characteristic of for a different type of process that contributes to creep. So you can use the value of Q to determine the creep mechanism. Q can be a diffusional creep, and that's usually if there's multiple ions that are diffusing, the slowest moving species is the one that's controlling the creep rate. It can be an activation energy for a viscous flow process, or an activation energy for grain boundary sliding, or an activation energy for dislocation motion. So one of the most common ways of creep that takes place in a refractory is by diffusional creep mechanism. Also, the viscous flow mechanism is quite common. So we'll just look at what's going on briefly in a diffusional creep process. And it turns out there's two types of creep processes, or two models that have been developed. One is grain volume diffusion, and the other one is grain boundary diffusion. So in Nabarro-Herring creep, the material, the atoms are diffusing through the bulk of the grains or crystals. And in Koval creep, diffusion is taking place along the grain boundaries. Both are diffusion mechanisms, but different paths. This is diffusing through the volume. This is diffusing through the grain boundaries where the crystals are in contact with each other. So let's look at a material when a stress is applied. And this is my drawing of a polycrystalline material. And then I apply a stress to that body. It elongates. And then we'll pull out an individual crystal and see what's going on with that crystal. So we'll look at how material is transported when the stress is applied to that individual crystal. And it turns out ions are diffusing from areas of compression to areas of tension. So here's an individual crystal that we pulled out. We pull it in tension. The Poisson effect is basically causing it to shrink or compress in the horizontal direction. And ions are diffusing in a tensile direction. So they're moving from the area of compression to the area of tension. So they're moving in the direction of the arrows. So area is taking from the side of the material, is taking from the area on the side of the crystal to the area on the top or the bottom of the crystal. So it's changing dimensions, it's creeping in the vertical direction. If you're moving material, atoms, or ions, according to these arrows, in the opposite direction, you have to be moving vacancies. So vacancies move from tension to the compressive areas. So vacancies are moving the opposite as the material, the atoms, or the ions. So this is diffusion through the bulk, Nabarro-Herring creep. Koval creep would be just taking these arrows and putting them on the grain boundary, material diffusing along the grain boundaries. So here's some values for N and Q that have been measured for different types of refractories. We have a 60% alumina brick, a 65% alumina brick, fused cast alumina, a Super Duty fire clay, a magnesia brick, a magnesia alumina spinel brick, a mullite brick, a silica brick, and a stabilized zirconia brick. So by the end of this course, when we go through all these compositions, you'll know exactly what these materials are, how they're made, and what their significant properties are. But right now, when you make these measurements, the end value is all about 1. So that tells you it's going to be a diffusional or a viscous flow creep mechanism. And these are the corresponding activation energies in kilocalories per mole, maybe from 36 to about 240,000 kilocalories per mole. So the stress exponent, N, is usually 1 for most refractory materials. That's telling you that most refractories creep by diffusion or viscous flow process. So when you get to high temperatures, diffusion of material processes become rapid, so material diffuses quickly. At high temperatures, you also form glassy phases, usually a silicate-based phase, and they become less viscous as you increase the temperature and become fluid. So both of these processes, diffusion or viscous flow, are the common mechanisms for creep and refractories. And because you can have diffusion and glassy phases present at the same time, you're usually having more than one creep process occurring at the same time. That's why it's rather difficult to separate them. Activation energies for creep, I mentioned, are usually maybe 100 to 200 kilocalories per mole. The range is typical for high temperature processes in ceramics. Different crystal structures have different activation energies for diffusion. They're usually in this 1 to 200 kilocalorie per mole range. And different compositions of these glassy phases, these silicate-based glassy phases, have different activation energies for viscous flow. So those activation energies are still in the same type of range, 100 to 200 kilocalories per mole. So it's because you have an overlap of activation energies and diffusion mechanisms, it's difficult to determine actual mechanisms that are taking place. So how does the grain size affect creep? Well, it turns out a smaller grain size gives a larger creep rate. So if we look at our creep equation and we hold the stress constant and the temperature constant, we end up with the strain rate, d epsilon dt, equal a constant times 1 over the grain size to the grain size exponent A. And again, K is the constant that it's incorporating the stress and the temperature right now. So the bigger the grain size, 1 over a grain size, so the bigger the grain size, the smaller the creep rate. So large grains give low creep rates. The diffusion distances become larger, so you decrease the strain rate. So ideally, if you want a material that's creep resistant, you want to go with bigger grains. Now, that's opposite to strength. We just described strength earlier this morning. Strength equals a constant 1 over d to the 1/2 power, and d is the diameter or diameter of a grain. So d is related to grain size. So 1 over grain size to the 1/2 or 1 over d to the 1/2 is the same thing. So here, you increase the grain size, you go to bigger grain size, you're going to lower the strength. So here it's desirable to have a large grain size to reduce creep rates. Here it's desirable to have a small grain size to increase strength. So it's opposite behavior between creep and strength. And this occurs for a lot of properties in refractories. You might like to optimize multiple properties for a particular application, but what it usually comes down to is you have to compromise, because when you tend to maximize one property like strength, you're going to minimize or you're going to increase another property like the creep rate. So that's pretty typical in designing a refractory material. You have to be aware of changing a structure to maximize a property, you may be decreasing other properties that you want to build into the material. Porosity also affects the creep rate. The creep rate increases with increasing porosity. Porosity simply reduces the cross-sectional area available to resist the creep. And this is another empirical equation. The creep rate, the epsilon dt, equals the constant, and that's divided by 1 minus p to the 2/3 power. So another empirical equation, k is a constant, p is the volume fraction of porosity. So as you increase the volume fraction of porosity, this strain rate increases. So increasing porosity increases the creep rate. Where do you use these? All the mechanical properties, elastic properties, strength properties, creep properties, research and development to improve performance, engineering applications, and design. You need this data to design a furnace. Quality control, all of these are used in quality control, and they're in data sheets for specifications. So there's a couple different ways of measuring creep behavior. The first one is ASTM C16. It's a relatively simple method. It's sort of a pass-fail method. It doesn't record the complete creep curve, but it gives you a measure of how well the material performs. So it measures the resistance to deformation of a refractory sample subjected to a compressive load, and all the refractories are basically put in vessels that are under compression. So all the creep tests are in compression. It's measured at some temperature for a certain amount of time. So you load a sample in creep, in compressive creep, you hold it at some temperature for a certain time. And then the decrease in the sample dimensions parallel to the applied load, and you have an increase in the sample dimensions perpendicular to the applied load. So basically, you're in most cases, you're decreasing the height of the sample and increasing the cross section. It may not be true all the time, because this is sort of like a reheat test. We discussed a reheat test yesterday. If you're running a creep test at a temperature higher than the material has been stabilized at, you have other reactions taking place besides creep. So you may have a reheat shrinkage or a reheat expansion superimposed on the creep mechanism. So if the material fails, it's usually a shear failure. So you run a sample at a temperature for a specific time, and if it doesn't fail, you measure the dimensions before and after, get the amount of deformation that has taken place, or sometimes it may actually fail, and it will usually be a shear failure. So it's an important test that measures the ability of a refractory material to withstand a load at an elevated temperature. So it's really a measure of the upper use limit of the material. It's a measure of its high temperature service potential. So if you have a significant deformation at a particular temperature, you probably don't want to use that material at above that temperature. It's commonly used to evaluate fire clay and high alumina refractories. It's used to evaluate refractory quality. If you have a poor quality material with, say, a great deal of impurities, it will not have a good hot load strength. Many refractory manufacturers include the C16 test in their data sheets. It's an easy test to run, and it's included in a lot of data sheets. the way this test is run, it's run on two 9-inch straights. So the length of the sample is 9 inches and the cross section is either 4.5 by 2.5 or 3 inches. So you're running 2 samples for an average. So here's a full-size brick standing on end. It's 4.5 inches in width and probably it looks like maybe 3 inches in thickness. You're applying the load in this direction in compression along the 9-inch length of the sample. So this would be 9 inches from top to bottom. You need a high temperature furnace, and the heating rates in these tests are quite fast. So you usually have a gas-fired furnace capable of going to probably at least 3180 degrees F. I think that's the highest temperature in these tests, but you can go a little bit higher than that in a gas-fired furnace. You have to have a loading device. You have to apply a compressive stress to the sample. And the test is run at 25 PSI as a standard load. You can run at any load you'd like, but it's 25 PSI is the standard. There's various types of furnace arrangements for applying the load and running the temperature up. So this is a direct load machine where you have the sample sitting here, 2 samples in the bottom. You have loading rams in contact with the sample, and then you have weights that are applying the direct load to these rams. So you vary the weights to get perhaps 25 PSI or whatever load you want. This is a side view, and the top view shows that it's a cylindrical furnace and there's 2 burners, so it's a gas-fired furnace. So that's one arrangement for applying a direct load to 2 samples in a gas-fired furnace. You can use a lever arm to also apply the load. So here's a lever. You hang the weights on the end of the lever. You know the length of the lever and the pivot point, so you can calculate the load you apply to the sample. So here's your sample sitting in the bottom of the furnace. Here's your containment furnace and your loading ram on the bottom and the top. And this one is another 2-position furnace with a cylindrical furnace with the burners. So it's a gas-fired furnace again. So how you run this test is simple. You measure the sample dimensions. You're definitely interested in the length change. You can also measure the width and thickness. You apply a compressive strength, and the normal load is 25 PSI. There's a different heating schedule for different types of refractories. So you heat it, you cool it to room temperature, remove the load, and measure the sample again. If the sample didn't survive, you have usually a shear failure mode, and you record the temperature where it failed. So this is a table from the ASTM test showing various schedules for running different types of refractories. So this column is hours and minutes. So elapsed time from when you start heating, and these are the temperatures that you should reach at these time frames. There's an 1.5-hour hold or a 90-minute hold on most of these. And the maximum hold temperature is shown here. This one is probably a medium duty fire clay, 2370. This is 2460. 2640 might be a super duty fire clay, and 2900 might be a high alumina. Same thing with 3000 degrees F. Schedule 4 and 5 are called tests of failure. So you just keep running the temperature up until you actually observe failure and then record that temperature. And when we talk about silica bricks, they have an interesting creep behavior. They actually creep very little up until the temperature they completely fail. So they hold their load rather well, and all of a sudden they develop a liquid phase and have complete failure. So usually silica brick are run to failure, and some other bricks maybe also be run to failure, MgO or chrome MgO type bricks. So you can either run it with a 90-minute hold, or you can run it with a failure. So you hold it at a temperature and get a deformation after the test, or you continue rising the temperature until failure takes place. You simply count or calculate the percent deformation. D is the percent deformation, is just 100 times the final length minus the initial length divided by the initial length. And a typical report would look like this. The surfaces that are loaded are diamond ground, so they're flat and parallel. Two lengths are usually measured on either side of the sample for an average. So you have length 1 and length 2. The width and depth of the sample, or width and thickness of the sample, is also measured. This was a 9-inch straight. Basically, it's a little shorter than 9 inches because it was surface ground. It's about 4.5 inches wide by a little less than 3 inches thick. You get the weight and calculated density, and this is the density usually for a high aluminum brick. The area, you want a 25 psi stress. That's the load to give you the 25 psi stress on this area. This was run with schedule number 6, which is this schedule to 2900. So it was run to 2900, and it was held for the 90 minutes or an hour and a half. And then after the test, the lengths were measured again. And this is what I mentioned before. This one actually is not negative. It's actually, the length is slightly bigger than when we started for all 4 of these samples. So what has happened here, the sample may have been creeping, but also there was a chemical reaction in the sample. And I suspect this was a high aluminum brick, and we were having mullite forming during the creep test, which causes an expansion. So it's pretty amazing that a new crystal structure can form and resist deformation and make the sample actually grow larger when it's actually loaded at a high temperature. So the growth of a second phase in this material was a little bit larger than the amount of creep that it took place. So this is the before and after test. The before results and after, you don't know really what's going on at all in between. But that's why I said it's a pass-fail test. But it's a test that's easy to run, and you can decide whether refractory fails or creeps rather easily. So before and after test, that's a test that's commonly used. The more sophisticated creep test is where you monitor the change in length throughout the entire test. So C832 is thermal expansion and creep of refractories. It measures the linear change of a refractory sample that's subjected to a compressive stress while being heated, and then you heat it to some temperature and you hold it at an elevated temperature. So you're continuously measuring the change in length of a sample that's in compression during the heating cycle. At the end of that heating cycle, you hold it at a constant temperature, and then you still monitor the change in length at that constant temperature. It's usually run in an oxidizing atmosphere, so it doesn't really apply to materials containing a carbon source like pitch or resin, any kind of carbonaceous bonds. You can do a creep test under inert atmosphere. It just requires a special furnace. So if you run it under inert atmosphere, you can run creep on some of these composite materials like an MgO carbon material, or a material containing silicon nitride, silicon carbide if it's run at a high temperature where you have an oxidation issue. You can run silicon carbide and silicon nitride at lower temperatures if you don't have excessive oxidation. So the test is simple. Samples are placed in a furnace. They're subjected to compressive stress. Sensors are positioned in such a way that you continuously measure the linear change parallel to the direction of the compressive strength. So you're continuously monitoring the length change. The temperature and linear change are recorded while heating the furnace at a controlled rate for thermal expansion under load testing. And the time and linear change are also continuously recorded at the soak temperature, and that's usually for 50 hours. So a usual creep test is run for 50 hours. You can run any number you want, 100 hours, 500 hours. If you have a very creep resistant material, 100 hours makes more sense. Some people run 500 hours to try to detect some creep. So a creep curve looks something like this. You have percent linear change versus temperature. So you heat up the material. Here's your linear increase in length. At some point, you're going to reach a maximum dilation temperature where creep starts, and then the sample length is going to decrease. So when you reach your hold temperature, at this point here, whatever that is, you hold the temperature constant, and now you monitor the length change as a function of time. So now you generate your 0 to 50 hour creep curve. So the maximum dilation is the temperature or percent linear change, where the thermal expansion rate now equals the creep deformation rate. So here the material is expanding at the same rate it's creeping. And that's sometimes useful. It's useful as an indication of where you might want to cut off the upper use limit. You might want to stop the upper use limit right there at that temperature, because after that you start having creep, especially if this is a significant amount of creep. What's usually reported is a 20 to 50 hour creep rate. This is a steady state region I mentioned. This is the primary creep region, and then you have a linear region, which is steady state. At some point in time, this will drop off and you'll have failure. So 20 to 50 hour creep is what's measured. You get a percent deformation per hour during that time period, a 20-hour time, 30-hour time period. So this test is important because you can rank different materials according to their creep rates or load bearing capacity, and you can use it to calculate lifetime predictions. You can get a creep rate and estimate how long your sample will last in service. This test, ASTM-C 832, uses a rectangular prism, 1.5 inches by 1.5 inches in cross section and 4.5 inches long. So you're applying the load to the 1.5 by 1.5 cross section. So here's a sample prepared for creep testing. It's 4.5 inches long, and the cross section is 1.5 by 1.5 inches. So for creep testing, your creep furnace should be a high temperature furnace, maybe 28 to 3200 degrees F. Furnaces, high temperature furnaces that are fiberboard lined with molybdenum heating elements can do this quite easily. A loading device, you have to have a means of applying a compressive stress, and 25 psi is the minimum on this 1.5 by 1.5 inch cross section that's specified in the test. We have samples that we run at other loads, maybe 100 psi, maybe 200 or 300. Just depends on how far you want to push a material. you need a sensor to measure the change in length. A common way is an LVDT, a linear variable differential transducer. That's basically the sensor in a dilatometer. And a method that we use is a laser extensometer. So you have a couple different choices on how to measure the length change. And here's a diagram of a furnace with an LVDT transducer. Your sample is right here. This is the containment furnace. You have a loading ram on the bottom, a loading ram on the top. And up on top here, above the loading ram outside the furnace is your transducers. So you have a rod that runs down to the bottom of the sample. It touches the bottom load block. And you have another rod that runs down to the top of the sample. And your LVDT or transducer is right here. So as you heat the sample and let's say it elongates, this rod moves and you record the change in the dimensions on the transducer. So it's relative to the bottom of the sample. And this furnace has two positions for two different samples. So this is essentially a vertical dilatometer. We described dilatometers yesterday. And I mentioned that if you have a really coarse grained refractory and you're running a dilatometer with a small sample, you might not want to do that to get a good result. This sample is quite a bit larger. It's 1.5 inches by 1.5 inches by 4.5 inches. It's a lot larger than the 2-inch by basically 1/2 by 1/2 inch sample in a dilatometer. So this is essentially a dilatometer. It calibrates the same way. You have to run a standard, get a calibration curve, and make a correction just like in a dilatometer. There's another way of measuring the elongation or deformation, and that's to use these rods. These are usually sapphire rods that contact the sample and measure the deformation between the contact points. So the levers come out of the furnace and they're connected to a transducer. So the spacing at the end of the levers, you can use that to determine how much the sample moves. That's actually a very good way of doing it. So here's your sample. You have levers in contact at both sides to get an average. And here's your load ram and your other load ram and then the containment furnace. And another arrangement here is this one is actually a smaller sample. It's a cylindrical sample. It's probably there's another version. Every country has a version of test specifications. There's a German version that's used quite commonly in refractory creep testing, along with this ASTM test C832. And it's a shorter cylinder. But you also have your rods in contact with the top of the sample and the bottom of the sample and an LVDT up on top here to measure the change in length, your loading rams. And this one is using a weight system with pulleys to apply an upward load on the bottom ram. The way we like to do it, I think it's the best way, is using laser deflectometers or laser extensometers. So here's your sample. Here's the loading columns. So you have a laser source. You shine it through the furnace, and on the other side of the furnace, you have a laser detector. So the dotted line would be the furnace. This beam is in the shape of a plane. It's longer than the 4.5 length of the sample. And what it does is it cuts off a region over here and over here. So what passes through is actually the length of the sample. The beam is not run through the sample, it's running along, in this case, along the side of the sample, let's say in the back of the sample. The load blocks cut off the beam. So the laser detector here detects the actual length of the sample. The advantage of this is that there's no calibration curves necessary. You don't have an LVDT, you don't have to run a standard, you just calibrate the laser and you get a direct measurement. It's non-contact, you don't have push rods touching your sample. So it's another way of measuring a creep. So I mentioned that if you have an LVDT, you have to do a calibration, just like we talked about for a dilatometer. You have to determine the machine output curves using a standard, a sample of known expansion. Calibration standards are usually MGO, AL203. If you have a low expansion material, you want to probably calibrate with a low expansion material like fused silica. You try to match the expansion of your standard to the expected expansion of your unknown sample to get a more accurate measurement. You determine the correction factors as a function of temperature, just like in a dilatometer. And the correction factors are just the algebraic difference between the machine output and the true expansion of a calibration standard. So that difference is added or subtracted to the actual curve when you run a sample. So the algebraic sum of a correction factor and the machine output of an unknown gives you the expansion of the sample. And that's where you use it during the expansion under load portion of a creep curve. The laser is non-contact and it requires no calibration except for the accuracy of the electronics for the laser. How you run this test, you apply a compressive load of 25 psi. You heat and cool it at a controlled rate. This test calls for 1 degree C a minute. So it's a slow heating and cooling rate. And you measure the linear change as a function of temperature, or when you're at a constant temperature as a function of time to get the entire creep curve. But on the linear portion, it's just a thermal expansion. And there's two ways of running this test. You can do what's called an EUL, an expansion under load. So test continues until the thermal expansion ceases and you have a maximum dilation level. So you might want to run the sample till you get 5% deformation, maybe 10%, or you may want to run the sample till you get complete failure. So you never stop heating and have a hold time on an EUL. You just run it up till you get a desired deformation or a complete failure. In that test, you get your maximum dilation point. You can run a creep test where you hold it at a constant temperature for the 50 hours. So you bring it up to some temperature, hold it for 50 hours, and now you record the heat up change and the change during the 50-hour creep. The percent linear change is the same formula for most of these tests, delta L over L0 times 100. So the change in length divided by the initial length times 100 to give percent linear change. And a test report looks something like this. This is an expansion under load test. It's a relatively low density material, 59 pounds per cubic foot. The stress is MPa, megapascals, 0.05. That should be 25 psi, and it was run up to 1600 degrees C. So at this temperature, 1321 on the way up to 1600, the expansion was 0.735. That was the maximum dilation temperature. So after that temperature, the sample started to decrease in length. And then the EUL deformations that were recorded are these are pretty common: 0.5%, 0.6, 1, 2, and 5%. So at these percentages deformation, you have a corresponding temperature. So at 0.5%, you had 14.54, 1454 degrees C. At 5%, you obviously have a higher temperature, 1544 degrees C. So the output of an EUL is the maximum dilation temperature, and then these deformation temperatures for these different percentages of deformation. We also measure the before and after length physically with a micrometer. And that just tells you you had about 15% total creep. It doesn't mean a great deal because that's heating and cooling, but we get that measurement. And the data acquisition system, in this case, the laser mic, the laser extensometer gives about 15.9. So it's just a way of checking to make sure the laser and the physical measurements agree. And this is the deformation heating to the maximum temperature, which was heating to the 1600 degrees C temperature. That's about 13.5. So another couple percent deformation occurred during cool down. So when you plot linear change versus temperature for an EUL, you get a graph that looks like this. So this is 0, and then this is the negative numbers for the deformation. So you get an expansion, and then you get your drop off as the length decreases and you have deformation. We mentioned that the maximum dilation point was 1321 degrees C. That's about right here. The computer program that analyzes this decided that was the maximum dilation. And the expansion was about 0.7%, which is about right there. And then these were the different percentages and the corresponding temperatures of deformation. And it's from the maximum dilation point. So 5% is about, it's not exactly at 5%, it's a little higher. So that should be about 1544 degrees C. And so that 5% is about here. So the test was run to 1600, and you can see there's a deformation up to about 13% right there. So that's an EUL. The other version is the actual creep test. This was a denser refractory, 177 pounds per cubic foot, 25 PSI, and this one was run at 1600 degrees C for the whole temperature. So in this case, the maximum dilation was just below 1600 degrees C, it was 1583 degrees C. So it just started to bend over as we approached the whole temperature for creep, and the expansion was 1.1%. So that's your maximum dilation. And then there's a lot of ways to look at the steady state creep region. This is the 20 to 50 hour creep rate. So this is average between 20 and 50 hours minus 0.309%. And if you do percent per hour, it's minus 0.0103. And that's just taking the point at 20 and 50 and drawing a straight line and calculating those rates, the percent and the rate. We also do a regression analysis in that time frame, and the regression gave us 0.29% during that 30-hour period and a creep rate of 0.0099. So almost the same as just reading it off the table. These are just different versions. There's a variety of tests. There's a DIN, a German test, an ISO test, and they all have different ways of reporting Some of these tests like to report a maximum dilation or 5 hours past the maximum dilation, 10 hours past the maximum dilation. So that would just be the percent deformation from maximum dilation to 5 hours, maximum dilation to 10 hours. Here's one maximum dilation to 20 hours, to 25 hours, and to 50 hours. And the ISO test likes to do a 5 to 25 hour deformation. So depending on what standard, you have all these different possible ways of looking at the creep deformation. There's also a before and after measurement. There's a before and after measurement from the laser acquisition system. And then there's a measurement during the heating to the maximum temperature and during the 50-hour creep hold. So a creep test would look like this: percent change versus temperature. Here's your heat up for this material. It's 25 psi heated to 1600 degrees C. A maximum dilation is right here, about 1583. You can barely see it just starts to bend over. And that expansion is 1.1%. So when you reach 1600, you hold the temperature constant and you run the time from 0 to 50 hours, and you get this type of creep behavior. So you can see that around 15 hours of creep, you enter the steady state region. So you have pretty much linear creep. So that's where your creep calculations come between 20 and 50 hours. So we do a regression analysis on these data points, and we get an equation. This is the regression equation. It tells us that the creep rate is minus 0.0099% per hour. And then if you also record the cool down, so this is the heating cycle. And now we just have temperature here. So this is the deformation during creep. It's roughly 1%. And then the cool down. So the creep that took place here, these are linear. You have about 1% over here. So that was the last slide on this session. Does anybody have any questions on any of these topics? Okay, we'll put these notes on the internet again, and tomorrow we'll combine thermal and mechanical properties and talk about thermomechanical properties, which is thermal shock, an important topic in refractories, and we'll also talk about corrosion. And that'll finish up 3 days of properties, and then on Friday we'll start on the different refractory compositions. It'll be silica refractories, and then the addition of alumina silica for the aluminosilicate refractories. So in each one of those, we'll talk about the raw materials. We'll talk about phase diagrams and phase relationships. We'll talk about how the refractories are made, how they're processed, and then we'll highlight how the microstructure affects the properties. We learned a little bit today how microstructure affects creep and strength and so on. So we'll tie this all together under each composition, each different type of composition refractories. So again, if you have any questions, you can call me anytime. You can send me an email. My email was in the original advertisements, but it's just my last name, Homeny, that's Homeny, at Orton, that's Orton, ceramic.com. So thanks for